Hello, and welcome to the third installment of our webinar series, Using Cloud-Based Virtual Screening to Find Novel Leads, Blaze in the Cloud. My name is Ray Lawrence, and I'll be your presenter for this series. During the video, should you have any questions, please note the slide number and send your query to support@cresset-group.com. For today's session, we'll follow an agenda that will cover the following: a review of Cresset's technology, specifically our field points, an overview of our products focusing on Blaze for 3D field-based virtual screening. We'll talk about using Blaze in the cloud, doing a practical demonstration and exploring the Blaze web interface. We'll talk about how Blaze searches progress, and we'll review some results. Cresset's philosophy is all about looking at ligands the way they are seen or experienced by the protein receptor. To do this, we step away from the two-dimensional representation and consider a ligand as something that has a three-dimensional distribution of shape, charge, and hydrophobicity. Comparing molecules using the full molecular electrostatic potential energy surfaces is computationally expensive, so we've condensed this information down to field points, which are placed at areas of local extrema in these functions. Blue corresponds to areas where electrostatics are negative, red to areas where the electrostatics are positive, yellow gives a van der Waals accessible surface area, and orange field points are in areas of hydrophobicity. The size of the field point corresponds to the strength of the field at that point in space. The presence of a field point suggests that this is an area of the ligand which may form favorable interactions with a protein receptor. It is noteworthy to say that just because a field point does not appear, it doesn't mean that there's no field at that point in space. It's simply that the field is not at a maximum value. With Cresset software, we use these 3D field point patterns to compare molecules in a biologically relevant way, the way a receptor would experience the ligands. For example, if we have the bound conformation of cyclic AMP with this field point pattern, and we have a synthetic analog that has an accessible three-dimensional conformation that has a similar field point pattern, then the receptor should see these two molecules in the same way, regardless of how similar or dissimilar their chemical structures are. This allows us to compare molecules at the bioisosteric level without bias. Going a step further, the technology can be used in the ligand design process for optimization or scaffold hopping, which is shown with the changes made to the center molecule to give the molecule on the right-hand side. We do these comparisons with 4 products. Blaze is used for virtual screening, which we will discuss today. Spark is for bioisosphere replacement and scaffold hopping. And Torch and Forge are used for design and understanding structure-activity relationships. Torch is a medicinal chemist tool. Forge is a computational chemistry tool. It includes additional functionality over and above the functionality that's available in Torch. The Blaze virtual screening experiment is a three-dimensional virtual screen in which we use the field point pattern as our query seed. The query molecule should be in a three-dimensional conformation, a bioactive mode, whether that mode was determined crystallographically or through pharmacophore templating. The query seed, the 3D field point pattern, is then used to query the Blaze databases, which consist of millions of molecules with up to 100 conformations of each molecule. The search can be quick, thorough, or exhaustive. The results are reviewed in their 3D orientations relative to the query, and it is expected that compounds with similar field point patterns will be found, regardless of their structure similarity to the seed molecule. As an example, some years ago, one of our academic customers did a virtual screen to look for new non-steroid chemotypes for 11-beta HSD1 inhibition, starting with the shown steroid as the seed molecule. In the output, there were 23 lead-like hits from 4 non-steroid chemotypes. The 3 sample structures shown include a structure that was similar to patents filed by AstraZeneca. The compound on the right was patented by our customer. The compound on the left was planned to be patented by our customer, but was scooped by Insight. In this example for CCK2 inhibitors, 100 of the top results were cherry-picked, of which 88 were purchased and tested. Of the 88, About 30 had lead-like activity in the low micromolar range and were in acceptable molecular weight range for optimization. For our virtual screening experiment today, we will use the bioactive structure of Boehringer Ingelheim's nevirapine. Nevirapine is a non-nucleoside reverse transcriptase inhibitor, which the World Health Organization has deemed an essential drug in combating the AIDS epidemic. Nevirapine is used in conjunction with other reverse transcriptase inhibitors to help avoid the HIV virus developing a resistance to the drug. The question arises as to whether we can use 3D field-based virtual screening to identify new chemotypes which reverse transcriptase may experience in the same way. Blaze can be configured to run at the command line level or may be run through the convenient web interface. The command line interface can be wrapped with KNIME or Pipeline Pilot or other in-house routing scripts. The Blaze search progresses as a multi-tiered approach, with each subsequent step of increasing refinement. The first pass is a coarse comparison of field prints, which quickly eliminates poor matches. This runs on 100% of the selected Blaze databases. The next pass is our initial 3D ligand alignment, which is a clique-based alignment. This protocol is run on 50 to 75% of the top hits from the field print pass. Finally, the top 5 to 10% of the clique search hits are subjected to the full ligand alignment with the simplex alignment algorithm. The ligand alignment algorithm in Blaze is the same as that in Forge, however, there have been some shortcuts included for speed. Blaze, of course, runs on both CPU and GPU clusters. Blaze in the cloud runs on our GPU cluster. So what we'll do is we'll get the experiment started and running, then we'll talk about what's happening during the calculation and explore the Blaze web interface. I've embedded my link to the Blaze demo server here, which we will click. When you launch Blaze in the cloud, we include a secure connection, HTTPS, and a username and password are required for access authorization. Since this is our Blaze demo server, we don't include that level of security. But I have chosen to preserve my username and password, but in the real world, I would never do this. Once the splash page loads, we see the main Blaze panel. On the left-hand side of the page, we have a gray button bar that helps us navigate the interface. To set up our experiment, let's press New Search. Like all of Cresset's software, Blaze is wizard-driven so that it tells you what to do at each step. The first panel asks us to import a query molecule in its bioactive conformation. I have nevirapine structure saved in SD format, which I extracted from the crystal structure 1VRT. So let me grab that file now. And then we press Submit, which takes us to the rest of our experimental setup. In the next screen, we are asked to check that our molecule is indeed what we want to search on. It also gives us the number of heavy atoms in our search query, which we could possibly use to reduce our search space in a virtual screen experiment so that the hits are similarly sized to the query. If we press View, we have the option of opening this reference structure into Torch or Forge to take a look at the structure and confirm that it is the structure that we want to use for our search. And our structure looks good. And we're also seeing that the field points are nicely distributed and associated with the functional groups as expected. So this looks pretty good. So let's close this. And now we can press Accept and Continue. Now we give our search a name. And we can assign it to a project. We can fill in some comments as well. So we're searching nevirapine with decoy and spike databases for HIV-RT. Okay, so that's good. Now we choose which databases we want to search. This is a demo server, so we have some stock databases that are decoys as well as hits. So we'll grab those HIV-RT decoys, and we'll also grab the HIV-RT actives as spikes. As mentioned earlier in the presentation, we set how our search will progress. There are three tiers of searching with increasing levels of refinement complexity. The first pass is a coarse comparison. The second pass, we calculate a percentage of the best scoring hits from the coarse comparison. In our case, we'll use 75%. And this is subjected to our clique refinement. Then we'll take 10% of the clique results and subject those to the simplex refinement. We have the option of setting how our molecules are compared. For example, we can choose 100% shape, which would create an experiment similar to a shape-based rock screen. We leave this as 50-50 shape fields, as this tends to give us the best results. We can also include field constraints. For example, if we knew that a certain field point in our query seed was absolutely critical for activity, we would set that field point as constrained, such that the similarity score would be penalized if that field point didn't show up in the alignment with any of the library compounds. And that's it for the setup. Let's press Submit to get this started. This run usually takes about 5 minutes without any server load. Since our server load on any given day can be unpredictable, I've chosen to set the experiment running and then talk about what's happening in the background. In our left-hand navigation bar, we can click View Results, where we can choose to look at the results of previous experiments or our current experiment. So what we see here is that the clique is running. And if we scroll down, we can see how far we've gone through the calculation. And in this case, our clique is finished and the simplex is running. We'll come back to this when the run completes. With Blaze in the cloud, you have the option of loading your own compound libraries for searching. Blaze comes with complete compound database management facilities, allowing you to create new search libraries and update compounds, subject of course to permission levels. You also have quick access to the Blaze user manual by clicking the Blaze user manual link on the gray button bar, and that opens the user manual into an additional browser window. You can also check the server status so you can see what else is going on with the server and see how busy it is. Finally, if we go over to the right-hand side and click on Preferences, there's some defaults you can set, as well as set the system up so that you can get an email when your search completes, and you can also control the permissions, so you can control who else on your team will be able to see results or submit projects. So let's go back to the presentation so we can discuss Blaze in the cloud. Of course, many companies purchase Blaze and host and maintain it on their own servers. However, other groups may not want to make the IT investment and prefer to have Blaze virtual screening for their project on a services basis. There are two ways Blaze can be provided as a service. The first is as a consultancy service. In this case, you would have the Cresset services team run your Blaze search for you. This allows you to take advantage of the Cresset team's decades of experience in large pharma and biotech drug discovery. We've completed over 100 projects across every target class with a rapid turnaround time. The other way you can access Blaze is cloud-based software as a service. In this case, you would run the Blaze search yourself using our cluster. We set up a dedicated virtual machine with a secure HTTPS connection along with username password access authorization. When the work is complete, you would simply notify us and we close that machine. The Blaze in the Cloud option provides a search database of approximately 10 million commercially available compounds, which we maintain and update regularly with vendor information. An important consideration in assessing the performance of any virtual screening method is the nature of the molecules retrieved. Looking at the top 500 compounds retrieved by Doc and Blaze, we examine the molecular weights against that of the search query. Blaze consistently returns lower molecular weight molecules, and there's only a slight increase in the molecular weight as the molecular weight of the search query increases. The fact that Blaze returns lower molecular weight hits is of great utility in virtual screening. These compounds are more amenable for hit-delete optimization and development. So let's go back and check on our Blaze run. So going back to our View Results panel, we see that our run is complete. So we've clicked on Simplex in this top bar here, and we see that we have the option to download the overlays. We can also investigate the clique results as well as the field print results. Before we download and look at the results in Torch or Forge, let's look at the enrichment curves. The top curve and the curve on the right are showing basically the same information. However, the top one is using a log scale on the x-axis. In this graph, blue is the enrichment factor, red is the pickup of spikes, and green is random performance. And what we're seeing is that our enrichment is much better than random. The graph on the bottom left also shows where our spikes, our known actives, come out, and we see early enrichment, in that most of our spikes show up in the top hits. So now let's download our overlays. And we'll download 1 to 115. There's only 115, so let's grab all of those. And it gives us the option to save this. And we'll save this on our desktop so we can remember where it is. I've now opened our virtual screening experiment results into Torch. We see that the first 3 hits are nevirapine and nevirapine analogs. These are spikes which were known actives in the data set. If we look through some of the non-spike hits, we see some interesting compounds that are structurally quite different from the nevirapine chemotype. These structures represent opportunity. At any rate, we see that many of the top-scoring hits are known actives, which shows early enrichment. And when known actives and hits of different chemotype classes show up in the top-scoring results, we have the ability to use the experiment to open up novel chemical classes for our target of interest. In practice, you would pick a number of these that you would consider to be your favorites. So let's just grab a couple of these, and you select favorites by clicking on the little star. And these favorites can be exported to an SD file where you could start ordering molecules for your hit delete optimization. If we scroll over to the right in this molecular table, we also see the compound collection and the compound ID information. And in practice, this would be your vendor collection as well as the vendor ID numbers, so to make the ordering process a bit simpler. To export your favorites to an SD file, you would do this from the File, Export, Export Favorites. So what we've shown today is our approach to 3D field and shape-based virtual screening. In our experimental setup, we showed that you have control over how the experiment progresses. In some cases, a shape-based search is appropriate, while in other cases, having a combination of shape and fields will produce more interesting and novel results. Our Blaze methodology has been shown to produce chemotype enrichment, with resulting hits having lower molecular weights, making them suitable for hit-delete optimization. Blaze can be run on a local cluster that you maintain. However, you may prefer to run Blaze in the cloud on our GPU cluster. In doing this, Cresset provides a secure private virtual machine to keep your data safe. You can evaluate Blaze using the Blaze trial server that I showed today. Please contact inquiries@cresset-group.com, or alternatively, you can visit our webpage and download access directly. In the meantime, should you have any questions, please don't hesitate to reach out to support@cresset-group.com. But before we go, I'd like to direct your attention to our field-based chemistry days that are taking place in June. One is in Cambridge, UK, the other in Cambridge, Massachusetts. More details about the scientific program and how to register and attend are available on our website. These days are open to Cresset users and non-users alike and include both scientific and training programs, as well as a social and networking component.